Okay. Good morning. Nice to see you all again. And today we're going to learn about generative model. It's going to be an introductory lesson. And before we start, I just want to thank all the collaborators that helped me create the slides and prepare. These are the guys, and I really thank all of them. Okay, so I was just kidding, because these are generated faces. They don't really exist. But still, I feel like they helped me. And what we're going to be covering today. So we're going to start with the basics, and you should know that for this class today, we do the introductory part, we do the basis, and then next week with Tali, you're going to deal with the advanced generative models and all the cool diffusion models and the cool stuff that you've probably seen a lot by now. So we're going to start with the goal and the motivation, and we're going to discuss the different the various methods for generative modeling that there are. And then we'll have a very brief discussion about a thing called variational autoencoders. And then we're going to spend most of our time discussing GANs, generative adversarial networks, and that's the main agenda. So let us start by understanding what is a generative model, what generative models actually mean. And when you guys think about generative models, and you've seen all the whatever DALL-E and music generation and the text generation, and so you think about all this cool stuff. But I'm going to ground us back to be a bit nerdy and explain the really lame meaning of generative models in the basic of it. And the basic is just that given some distribution of data, a generative model would be able to just sample new instances from the supposedly distribution that the data induces. Okay? And why would I want to do this? I can do this to images, to text, to audio, whatever, to many other things. And there are many reasons I would want to do this. So back, I would say a few years ago, when I was giving such a class, it was very important to explain the motivation. I kind of feel it's not as important today after you've all seen what generative AI is capable of. But you know, just as a brief, so it's okay. The first thing is really cool, but you do content creation, and today you can generate images and videos and audio, and this is super useful, and people use it for any content they need to do, and they do it in computer graphics, and they do this to edit images and to process images, do things like denoising and super resolution. Things like this are also used, and simulations. But there is a main message that I want to make today. You're going to do all the cool stuff, all the graphical stuff. You're going to see them slowly, and then next week we tell you you're going to see a lot of the cool applications of it. But today I have this secret goal that I will try to convey while we do this class, and that is this principal idea of generative modeling is that whenever you solve a problem, and this problem might have more than one plausible solution, if you train to find just one solution, you're going to be lying to yourself, and you're going to produce some things that are some kind of average that might not be right. We're going to see examples of this, and we'll discuss this. But the thing is, the generative model would be the go-to whenever the solution is some kind of a distribution of possible solutions. And most problems in AI and in life, they don't have a single solution. They have a distribution of solutions. Every possible solution has some probability. Okay? Even your daily life problems, they don't have one solution, right? They have this distribution of solutions. Okay, so to start with, because everyone do it here is something that the generative models do today. I just did it with DALL-E 3. So I used the prompt, a bunch of students trying to figure out what generative models are. So this is you, okay? And let's discuss the generative methods. So there are three, I would say, main approaches for generative modeling, and we're going to see an example for each. So the first one is called parametric distribution. Then there are the auto-regressive models, but we're going to spend about 90% of our time with the last option that is called latent space mapping. I'm not specifying exactly what each is now because we're going to go through them. So here is the first approach, and this is called parametric distribution estimation. And the idea of this is that you're actually explicitly going to calculate what the distribution of the data is. You're going to fit some distribution, and I'm sure you've all seen methods that fit distribute, maybe not all of you, most of you have seen methods that fit distributions to data, right? So this is sometimes you do this estimation, and you do some assumptions, parametric assumptions. So one of which can be that under certain conditions, I know that my data needs to be a Gaussian. I'm sure you've all done this at some point of your life. You knew that your data should be normally distributed, and you say, okay, then all I have to do is find two things, right? If I want to fit a Gaussian to the data, right? The mean and the covariance matrix, if it's a multivariate. Yeah.
Is this different from what we got regression in the first two lectures or so?
Yes. I mean, why would you think it's the same?
You're feeding a curve to.
Oh, I see. Okay, so in regression, you don't have distribution. What you have is labels and inputs, and you find matching between inputs and labels. You don't have labels here. All you have is data, and you're trying to find some distribution that matches. So if you know your data is normally distributed, it's very easy to fit a Gaussian. But then if the data is more complicated than this, then there are some other methods. One of them is called GMM. Maybe you bumped into it. It's called Gaussian mixture model. And it's sometimes can be very efficient to assume that my data is made of this bunch of Gaussians. There are many reasons, like in nature and whatever. And if you use many Gaussians, then it can be pretty specific. And so let's see how it works as a, so maybe you've seen this, people sometimes use this as a clustering algorithm. So you cluster data, but this can also be used as a generative model. Let me show you how. So let's say I'm getting, this is the data that I'm seeing now. So the first step is just observing these samples. So I sample from some distribution, or I get the data set. The second thing is I assume some GMM, so a Gaussian mixture model. So in this case, you see it's a sum of some pi is some weight, and the sum of all these pi's needs to be 1. Of Gaussian, like a normal distribution with some mean and some covariance matrix. So the mean, it's a multivariate, it's in many dimensions. So the mean is a vector, and the covariance is a matrix. And there is a weight. So if I assume, I pre-assume the number of Gaussians. If I assume that I have n Gaussians, then I will have n scalars, n vectors, and n matrices. These are the parameters of the distribution. So then I have to perform this process of matching. I'm not getting into it. It's very nice based on expectation maximization tool. Those of you that have not seen, it's kind of, if you've seen k-means, so it's kind of similar to the way you do k-means. So each point has some relation to each Gaussian, and then you move the Gaussian parameters so that they fit their data better. That kind of it's like a smooth k-means idea. Okay, so you do this process, iterative process of finding the best parameters for the n Gaussians to match your data. And so now you have this distribution that you know that this is the distribution that we estimate that this data came from, and then all you have to do is sample. You just say, you know, you sample from a Gaussian, from a not a Gaussian, from a Gaussian mixture, from the distribution. Okay, so you sample out of it, and then you get new instances. Okay, so this is an example of parametric distribution estimation. Okay, it's distribution estimation because I explicitly calculate what the distribution is, what I think it is, and it's called parametric because I assume that the distribution is something I know, and the only thing I don't know is some parameters that describe. So in this case, it was these means and covariance matrices and the weights file. Okay, there can be other things. Sometimes, you know, you do it in small scale many times in science, right? You have you do some, I don't know, physics experiment, and you know that the distribution has to be whatever, some kind of exponential, and then you take your data and you fit. Okay, I'm sure you all done it like in Excel or something, fit. Okay. So this was the first approach, the parametric distribution estimation. And then there is the autoregressive image generation, which you've seen the autoregressive approach, I think, with Shai. Did you discuss recurrent neural networks? So you've seen that you do this recurrent neural networks, and you do sampling, right? There is softmax, and then you don't just take the max. You sample out of this softmax distribution. Are you with me? Are we good? You know what I'm talking about? Great. So this is a type of autoregressive generative model, and the sampling part is especially important there. But you can do this also to images. So these are just old examples. So back in 2016 already, this is called pixel RNN from Van der Oor, that's done many nice things in generative models. So you sort of do the same thing you've seen like with characters with the text, but in this case it's kind of you just calculate pixel by pixel, and then like the conditioning for each pixel is those pixels, the one above it and the one to the left of it, and then you slowly generate all those pixels. And there is also a pixel CNN, which is autoregressive. It's kind of similar, but kind of a bit more elegant, as it sees this controllable size of a window, kind of like CNN, but it's what we call causal, because you sort of, if this is the future of the generative process, you can't see the future, you can only see the past. So you train it the same way. You've seen like the sequences which like the text autoregressive models, and you can do it this way. And there are many other cool things. There is a pixel transformer from about 2 years ago. So basically the same idea, but you use a transformer, and then you don't have to kind of sample. So you don't have to do this. You don't have to do this like this. You can sort of try to estimate all the pixels together, and then you only take those that you get very high probability to their estimation, and then it kind of shows it all over. And there is a very famous and new autoregressive model, which is both autoregressive and kind of the next thing we will talk about, which is latent space mapping. But this is the diffusion models that have made a big revolution lately. And I'm not going to get into it because you're going to discuss this next week with Ali, but this is also an example for a very recent autoregressive approach. Okay. So these were two approaches that we briefly mentioned. And from now on, we will discuss only the third approach, which is called latent space mapping. And here is how latent space mapping works. The basic idea is that you have some kind of what we call a latent space, and this is going to be a controllable distribution. So the input is going to come from a distribution that I can freely sample from. So for example, in most cases, this is going to be just standard normal distribution, like with the mean of 0 and the covariance matrix that is the identity, okay? And I can sample from this whenever I want to. And then there is going to be a deterministic mapping function Okay, the randomness happened here and I sampled. And then there is a deterministic mapping function that maps instances from this domain to instances here, which is the data space. So one underlying assumption or a way to imagine things before you deal with generative models is that there is the entire space of all the things that could be. So we like images. So think about, I don't know, 200 by 56, 256 by 200 by 56 image. So you have this huge vector space with 256 by 256 by 3 dimensions, and anything can be in it, but only a very small portion, a very small manifold in this space is natural images, is images you will be happy with, is the images or is the distribution of your data set. So far we're good? Okay, because if I just all day just randomize numbers like 256 by 256 by 3 numbers, I'm not going to get an image, right? I can do this all day and I'm not going to get an image. But so there is this small space where those images exist. And what I want to do is that whenever I sample something from some other normal distribution, not in the same dimensions, not anything, this function will map me to some point in this domain. And when I take the probabilistic interpretation of this, I'm trying to think, what would I try to maximize? How can I say that this mapping worked well? How do I know that it did? And the most basic criterion to think of is what we call likelihood. Likelihood, if in, say, an estimation theory or whatever, is basically like saying, I have some kind of an estimation of a probability function, of a probability density function or whatever. I have an estimation of it. And the way for me to test if my estimation is good, because I don't know, nobody gives me and no one will ever give me some kind of ground truth distribution. There's nobody that's going to come, you know, the data I gave you, this is supervised learning and the distribution is actually 7 Gaussians and these are their parameters. That's not going to happen and the distribution is not going to be Gaussians, unfortunately. So what can I do? I'm going to take the real data instances, the data set that I have, and if my estimation of the distribution is good, it's going to grant high probability values or high values in a PDF, in a probability density function, to the real data, right? The distribution of reality, the probability of reality should be high. And this is what we call likelihood. I believe most of you have bumped into it, okay? This is like a nice way to think about likelihood. Likelihood is the probability of real life, of reality, which should be high. So say I somehow estimated the probability density function or not density if it doesn't have to be continuous, the probability x, the probability p, sorry, of x, and x is some real example. I want this to be high, but now I can use like basic probability to analyze this expression. So I think about the latent space, which I mark with z, and I use this simple Bayesian fact that the full probability of this x, I can write it as the probability of x given z, okay? But when I integrate over all the possible z's and take their probability, right? You've seen this margin. This is like summing all the marginal probability to get the full probability, right? Basic two-dimensional probability thing. Okay? So I can look at this integral. And why am I showing you this integral? Because this shows us exactly what we have here. Because P of z, we already said, this is like the distribution of z is a controllable distribution. Probably this very simple Gaussian, like with zero mean and and the identity covariance matrix, like variance of 1 to all dimensions. Okay?
The latent space in this case is one image.
No. The latent space is a normal distribution. You sample like a vector from a normal distribution. Yes.
Why is it dependent on theta?
It depends on what your model is. So in some cases it could depend. So there can be like some parameters that would be.
But it would be a different theta than p theta of x.
Not always. No, it can be always. But like for the simplest case, you're right. I couldn't do this and just say yes. Okay.
Well, the latent space is the number of dimensions is maybe the number of pixels.
No, doesn't have it. Usually no. Okay, usually no. Usually, so for images, in most cases, this will be like, you know, the number of pixels, whatever, and it will be like a tensor, like we know from CNNs and whatever, and here you'll have like a vector. So it's going to be less dimensions, which makes sense in some philosophical way because I just mentioned that this the size of the set of plausible images is much smaller than the entire space. So you don't need to have this high dimensionality of noise sometimes. Okay.
So the latent space is the data that you have?
No.
I don't get what this
The latent space is nothing. Is you sampling, you have like a controllable distribution, say Gaussian, and you sample. You write something like torch.rand, and you get values. Okay, that's what the latent space is.
And then I check the mapping from that to the data space and check that it falls with the distribution that we guess for the real data.
You can't really check, but this is some kind of what you want to achieve. Okay, you want to get the point in life that you want to get to is that you sample a vector, a random vector. You know what? One click takes less than a millisecond. You get a vector. Then this vector is mapped to some kind of, say, a nice image. Okay, this is what you want to get. So the latent space is a bunch of other things you can sample. You map it deterministically, and you get an image. So I was saying, so the P of Z that you see there in the integral is this latent space, and then P of X given Z is this mapping. Okay, I've given you a Z. Now, what's this P of X? So in many cases, this can be deterministic. So once I have the conditioning on Z here, this can become deterministic. Like the distribution is 1 for one possible solution and 0 for everything else. Okay, but it does, but not always, but some. Okay, so you get the idea. This is kind of tells the stories of latent space mapping it as generative models, and these are most of the modern methods are based on it. Another notion that I want to cover is called auto-encoders. Maybe you've seen this. So an auto-encoder is a very nice idea, and so this is this unsupervised thing where you have a network or some other mapping, and what you want is the output to be the same as the input. So your loss is going to be some kind of MSE or L1 or whatever between the input and output. And the point of it is that sometimes it has to go through a bottleneck. So in this picture, the bottleneck is spatial. So you kind of need to go to lower resolution and then go up or something. But the bottleneck can be made of other things. It can be made by noise or whatever. Okay. And the challenge of reconstructing the input it can be sometimes you could say why would you want it? Why do you need something that maps something to itself? And the reason is that in the middle there is what we call the code or the latent representation. And one thing you can think of is when you want to have like a more compact representation. So say that you want to compress data. Okay, so this basically, you just learned how to map many pixels to just a few. Okay, and assuming you could do this good enough, it's kind of a compact representation. So think about it, that if it would be linear, if it was just like the encoder was a matrix and the decoder was a matrix, then the best linear solution would probably be PCA. Okay, but this doesn't have to be linear, so it can do really nice things. But the reason I'm mentioning autoencoders, which are extremely useful and are used for many, many things, is to raise the question whether or not an autoencoder is a generative model. And what I mean by this is, let's do this thing. It's a nice idea. I train this autoencoder, say on these MNIST digits. You've seen these MNIST digits before, right? So I train this on these MNIST digits. And the question is, okay, now I'm going to take only the decoder and tell these less dimensions. And as the motivation I mentioned before, you know, the manifold of the data is much smaller in this space in some kind of non-linear fashion. So I'm just going to now randomly sample values, like a vector matches this side. And I'm hoping maybe that if I just random from some normal distribution, because this decoder has always been trained to output MNIST digits, so maybe whatever I put in here is tight. So whatever I put here, I'm going to get a generated data. Any thoughts? What do you think?
It says the distribution of the latent space is such that if you just sample, you'll get what you expect.
Yes. You're exactly right. I'm going to show some evidence supporting what you just said. So, okay. So this illustration, it's not an illustration, it's actually data from an experiment. So this shows what happens if the bottleneck size is just two values. Okay. So MNIST is what, 784 values, and you go to just two values, and you kind of see what's happening here. So the different colors mark the different the classes, like the different digit classes, and you can see that it's spread very, very widely. And so sure, if you fall like in this area, you're going to generate something that is probably the digit one. But look how big it is. And if I take some kind of a normal distribution and I sample from all this thing, I'm not going to get generated data. I'm going to fall in places that don't seem like they match this distribution. And the reason this thing is happening to me is because I only got one side of what I need. What I needed to get. So it's true. I trained this autoencoder so that it generates the only outputs it has learned to do are from the data. That's great. But what about the input to the decoder? Was it the distribution, the control distribution, the normal distribution? It was not. Okay, I don't know what it was. Basically, all I did is translating the generative problem that I had from the output space to the latent space, because I just now, so the next thing you would say, okay, let's find a way to find what the distribution of the latent space is. Okay, fine, that's exactly defining a generative problem, and I'm back again in trying to solve, find a generative model to do this, okay? So autoencoders out of the box, they're not going to be your generative model. What can be your generative model, okay, we said this, is this nice idea and one of the first serious generative models in the era of deep learning, and this is called a VAE, Variational Autoencoder, and it's built as an autoencoder, it has a lot of math around it. We're going to cover kind of the intuition, most of the intuition. There are two differences from a regular autoencoder. The first difference is that I'm going to use this sampling mechanism in the middle. So I'm not going to just encode, map it to something, and then decode. In the encoder, I'm going to do randomization. So the encoder is not going to predict the actual code, say. What it's going to do is it's going to predict a mean and a set of, like a mean vector and a set of variances. So think about it as a covariance matrix, but that is diagonal. So it's only, so it's like only predicting a set of variances for all the dimensions. And then I'm going to sample out of this Gaussian distribution, and this is going to go into the decoder. This is one difference that I have. The second difference is that I'm going to add another loss, regularizing this thing. I should mention, I don't know, people talk about it a lot. I find it kind of not a super impressive and interesting thing. There's a thing called the reparameterization trick. So how do you sample in a network? Okay. So if you, so think about it. If I just do, if I stop there and I do random, so it's not differentiable. How do I take the gradients? So the idea is that the way you do this is that you predict, what the encoder predicts is the mean and the variance, okay? And then you simply sample a number from a standard normal distribution, okay? So this, no gradients need to go to this thing. It's just a simple sampling mechanism. But then the trick is you multiply this number by the variance, and then you add it to the mean, and this is how you shift like from. So basically, what you actually sample is a standard from a standard normal distribution, but the reparameterization trick makes it to as if you sampled from your normal distribution with your mean and variance, and you can see in red it's kind of it's the back propagation, and you can see there's no problem. So this is just addition. So no problem for back propagation, and then it goes here. It's multiplication, also no problem. Okay, so you get gradients that go both to the mean and the variance. So this is how it works. So this is one difference that you have from a regular autoencoder. Yeah.
Each node there is a sigma of all the input, and also there's a mean of all the inputs that come.
No. It's a mean of. It's not a mean of all the input. It's just you predict some mean, some vector of means and some vector variances that for a given input you're going to do sampling, okay, and then it's going to get into the decoder. So every single input by itself is going to produce a different mean and variance. Okay. It's just you kind of interrupt in the way. Instead of mapping to something and then go, you say, no, I'm going to randomize things. The only information you get from the encoding is mean and variance, but now you're going to sample. Okay, so reconstruction is going to be much harder now because there is noise involved. You have a question?
Yeah, I suppose some people probably looked at the means of cell classes. Would we want the same instead of the belong to the same class to our closer means? Or?
This usually happens. Sometimes it depends on the some data don't have classes, but generally yes. Generally, you'll see in a minute that it does. So this is one difference from a regular autoencoder, and there is another difference, and which is we add another loss. So it's some kind of regularization. Then this is like the main point here, and it's called elbow, which is evidence lower bound. We'll explain why it's called this way soon. But basically, before I'm going to show you some pieces of math, but I feel like people go into this math and they get lost. But really, the intuition here is there is like a high level intuition that works. So So what you're going to do is you're going to encourage the distribution to be standard. So why would you do this? So think about what we've seen. Remember how it was spread, the latent space of the regular autoencoder was spread all over. But what if I regularize it? I'm saying it has to look very tight, like this standard Gaussian. So I basically explicitly approach the problem that we had before, which is I can't control the input distribution to the decoder. Now I can. I'm going to regularize the latent space of the decoder to be a normal Gaussian distribution. Okay, makes sense? And the way I'm going to do this is by, yep.
Sorry, I'm not sure I understand. Is this POC regularization, is it happening at the mu signal layer or at the sample layer?
Yeah, so I'll show you right now. The way I'm going to do this is by Kullback-Leibler divergence. So if you haven't heard of it, you probably heard about it very soon in some courses. It's a measure that it measures distance between distributions. Okay, and the nice thing is that all I have here is Gaussians. So this distribution is a Gaussian because I explicitly make it so I have a mean and the variance and I sample for it, and I want it to be close to a Gaussian. And then KL divergence between Gaussians has a closed form, which is very nice, and this is the loss. So this is to your question, this is the explicit loss that I'm going to use, is that I don't look at the samples at all. All I have to look is at the predicted sigma and mu, okay? And I just add another loss other than the reconstruction that says that sigma square plus mu square minus the log of sigma minus 1 has to be as low as possible, okay? And then this effectively encourages for each instance separately to be close to the standard normal distribution. Okay? These losses, they have a bit of this contradiction because say this loss got its way. Say it works perfectly. This loss is at minimum. Okay? It basically means that all the instances are mapped to zero mean and to variance of 1, which basically means I destroyed all the information that could help me reconstruct because they're all the same now. Okay, and it goes the other way around. If I'm able to reconstruct, it kind of makes these losses work harder. Okay, but the idea is that you reconstruct as good as you can while keeping all these numbers small. You keep so there is some kind of clue, some kind of information for an instance in its mean and variance that would, mostly its mean, that would help map it, but it can't be too strong. It needs to be close enough to be mean 0 and variance of 1.
Can you explain the mean and variance of what is estimated?
It's not estimated. It's
Predicted.
So the encoding works as instead of just encoding, you encode mean and variance, and then you sample.
Mean of variance of what?
It just you predict some numbers, then you use these numbers, and it's kind of before you use them.
Mean and variance.
It's not mean and variance before you used it. So you just predict a bunch of numbers. Then you take these numbers and you say, this bunch of numbers that I got here, this will be the mean. This bunch of numbers I got there is going to be the variances. And what makes them, gives them the respect of being mean and variance is that now I'm going to sample from a Gaussian distribution using them with this process here. Okay, so it's kind of like the encoder tells you, it's like I'm asking you to sample from a Gaussian distribution with mean of, I don't know, 5 and variance of 3. Okay, so you can do this for me if I ask you to. So the encoder provides the mean, those numbers, the mean and variance, and then the sampling process uses them to sample. Okay, and since I know there are mean and variance of this sample that is going to come, I know that when I talk about the distribution of what's possibly going to happen after I sample, this distribution is characterized by these statistic moments, which I can now judge the distribution using them because it's a Gaussian. So I know that if I want the Gaussian distribution that I get to sample here from, I want to be close to the normal one, I can just use these parameters that I know that it came from. Yes.
You use each loss to train a different part of the model, like one for the encoder and one for the decoder?
There's the old system, and the reconstruction is kind of, it uses everything, right? So the gradients go all the way, go like this. But then this regularization, it's connected here, so the decoder cannot affect this.
So then you will get like 2 gradients for each.
Oh, you're wondering how can you have 2 losses?
Yeah.
Yeah, you always have it. You don't really have 2 losses because in real life, what you're going to do is the final loss is just this loss plus that loss multiplied by some weights. This is all. People will sometimes say things about many losses, and the true interpretation of this would be that there is one loss, which is the some kind of weighted average of that. Yeah.
So we get the loss for the scale divergence, and we don't pass it back at the latent space. We pass it back at the reconstruction.
You don't have to worry about passing or not passing because it's just that the elements in this loss, just that they are here. So whatever you do when you take like the gradient of these things, it doesn't involve anything here. It shouldn't bother you. I mean, if it needed to use them, fine, but it does. It's just the fact that it doesn't. Okay. All right.
Some parameters are independent, right? The covariance
Independent between what?
between them.
Between different instances?
No. The covariance of the sample parameter is diagonal, right?
Oh yeah. This is why, because I guess I'm sure someone somewhere made a version of it where you predict the matrix and it's a covariance matrix, but they just did it much simpler. It's like the covariance matrix is diagonal and you only predict the variances on the main diagonal. So just to show you how it works, how it looks like. So this is what you've seen before, how it was spread, and this is how this latent space. Again, I'm reminding you, it's like a latent space of just 2 numbers. So this is what it looks like in VA. And it's important to check out the scale here because these images are different scales. So this goes like, I don't know, whatever, 25 minus 15, and this is like minus 3 to 3. So if I would put this on this picture, it would look like something like this, right? Maybe like this, okay? And very dense. So and kind of looks, Gaussianish. So if I sample from any point using just a normal distribution from this space, I'm going to be able to generate real images. There is a mathy thing, and we think about this data likelihood, and now we can think of this probability. So we have the encoder, and the encoder provides us mu and covariance depending on this x. Okay, you get some images as input, and then it gives you these statistics, and then you have the decoder, and the decoder, you could have imagined that it also does the same thing. So given a latent, it gives you mu and covariance, and then you would sample out of it. But the thing is that when you use reconstruction loss, when you want to sample out of it, the best thing you can do if you want to get your best sample from a Gaussian is you just take the mean, like with the highest value of the PDF. But we have to remember what our goal is. Our goal is, and this would make sense of the math. So our goal is that the likelihood will be the highest. So the probability of the real life, of the probability of the real data set of the images that we have should be as high as possible. And it's very common to look at the log of this probability. Log is monotone, so log of the probability goes high, it's the same as the probability goes high. Okay, so this is what we want to achieve. Okay, so basically this means we don't know what this P is exactly. Okay, it's some kind of distribution, right? That is hiding, because we know how to sample, but we don't have, like, we can't say what the distribution is, but we want to be able to check that whatever the underlying distribution, estimated distribution is, it gives us the highest probability for the data that we have. Okay, and so we can take the decoder as this is the part that generates, right? It's given this we do know. It gives us x given z. Okay, so we not exactly, because it's not like we really have this number here given that, because what we do in the decoder, we just only take the mean. But if we didn't take the mean, if we would have also in the decoder predicting variance and mu, then we could say sort of we have this parametric distribution here. It's a Gaussian, and we can use it. But this is where the decoder is, and then the P of z is just this normal distribution. So in inference time, you just throw away the encoder, and you only use the decoder, and then you sample from a standard normal distribution. You sample a z, get it into the decoder, and you'll get your generated image. Now there is this thing here, and also it took me longer than I thought. You can go through it, but the main idea is that we look this all creepy thing you're seeing now is we start from the probability, from the log probability. This is something that we want this to be as high as possible, right? And you do all these Bayesian tricks. Mostly is that you forcefully get z into the picture because you only have x there, right? But now you can get z using Bayes rule. Okay, you split things. Nothing is too hard, and you need to get to the final line. You have to kind of to know the definition of KL divergence. If you don't, so basically the KL divergence is the expectation of one probability divided by another, and the expectation according to this distribution that's in the numerator. Okay, you end up with these three expressions when you want to maximize these things. One of them is this scale divergence between things that you cannot calculate. You don't know what to do with this. It's intractable, but we do know that scale divergence is always positive. Okay, so this can't be negative. This is 0 or more. Okay, and you have this expression, which, look at this. It's log of p of x, specific x. Okay, one of the instances, given z, that was also, if you look at expectation, was predicted from this specific instance. So basically, you're saying the probability of predicting the instance that gave me z, and now decoding back and get it, should be the highest. This is basically the reconstruction loss. So if this is high, it means that the MSE between the input and the output of the autoencoder needs to be low. Okay, it means that I'm doing good reconstruction because x gave me z, now z gives me x, and given the z that x gave me specific x, I want to be able to predict that specific x. So the probability that I predict that specific x is high. So this is actually the reconstruction term, and it matches exactly if I just take MSE between the input and output, they would both go up together or down together. And then this second expression, if we look at this, it has a minus sign here, and this is the KL divergence between so this Q is the encoder. Okay, so it's the distance between the probability that I get for z given x the distance from this distribution to just the distribution of Z. Just the distribution of Z is the control distribution, okay, that I want. It's the normal, standard normal distribution. So this is just what we've seen before, is the regularization term saying that that I want the distance between the distribution of Z and the predicted distribution of Z and this control distribution has to be minimal. So it has a minus sign, and this is, and why this whole thing together called elbow evidence lower bound. The lower bound is because of this expression, because I don't know what this is, but I know that this is positive. So if I look just on these two, I get this up and this down as much as I can. I get only these two. What I actually end up with is saying what I have is the lower bound of the likelihood. The likelihood can't be lower than this minus this. Okay, it can be higher if I'm lucky, maybe this is high, okay? But I can't control this. So this is why what I optimize is the lower bound for the likelihood of the data. Okay, this is kind of the underlying math. And the generated data is just, okay, what you do is you sample, you get into the decoder, and then you can, if you do this again with just two values for MNIST, it's like a nice experiment to do. You can look at the latent space, and it's kind of nice. It has this continuous property, and these are some faces that you can generate, and you see, it tends to be kind of blurry. In VAE, this is 2014. Can you close the door, please? Thanks. Okay. This we've seen. Okay, I'm going to start with a question. I'm going to suggest a generative model for all of you, and I want you guys to tell me what you think about it, okay? So here goes. Basically, what we want is to map some noise from the latent space to real images, right? So here is what I'm suggesting. I'm going to take to just sample random noise. I'm calling it Z, and I'm going to sample a random instance from my data set, like an image. Okay? And now all I have to do is having some kind of a network. This is the input, this will be the label, and I'm going to train supervised learning, just some kind of a neural net, whatever your favorite architecture is. And I'm going to use an MSE loss between the predicted image and some instance from the data set. And here goes. This is everything we wanted, right? So I have a deterministic neural network taken from noise to images, and I just I just sample an image, sample a noise, and then all I have to do when I want to generate is just, I train this for some time on the data set, and then whenever I want to generate a new image I've never seen, I just sample new noise, getting into the neural network. What do you think? Good? No good?
Force the network to memorize random embeddings to real images without having the random and the images being closed in a sense. I mean, you want that similar embeddings will come out with similar pictures. And here it's just, there's no.
Okay. Yes, you're on the right track. So, yeah, I was telling you, this is no good at all. This can't work. This is not a generative model, and you cannot do generative things with non-generative models. And let me explain what is going to happen if I do this. This is what's going to happen. All right? I sample from this Gaussian, right? And there's the data space. And let's say I sampled my first noise, I mapped it to the data space, and I get this point on the data space. So far, so good. This is a real image. Everything is nice. Then I sampled again, and say I get a noise very close to the noise I sampled before. But I sampled another image from the dataset, which is far away. And here's another thing that happened. I got a whole other noise far away from these noises, and it got me an image, maybe the same image from the dataset that gave me this noise. My point here is that when we train things, we look at the expectation of training. So think about it like the ideal thing, and what we always optimize for is that what if I train this for infinite time? Okay? And if you want, you can even have infinite data, like all the data, like the data in real time sample from the real data distribution. Okay? Infinitely, whatever you want. Okay? Eventually, every possible noise is going to see every possible image, right? If I do this for infinite time. Okay? So everyone is going to meet everyone. And I'm using MSE. What happens when you use MSE or whatever other deterministic loss you want to do? Any idea? You just go to the expectation, to the sampling. So I don't know if you know this, but like the center of mass in physics or the expectation in probability is where you minimize the MSE, like the quadratic distances from all the points. So the best possible solution, what you optimize, your objective that you're optimizing will be minimized when you get the center of mass of all these images. So you're going to end up with whatever noise you produce, getting some gray, probably grayish image, like the mean of all the images that you have. Okay? Are we good? You understanding me? Okay. So it's like say I need to sample a number which is either 1 or 0, but then I use some kind of an MSE to try to map it. Okay? So I have a coin toss. Sometimes it's heads, sometimes it's tails. And on the other side, I sample sometimes 0, sometimes 1. And I'm going to match them. So the first time, heads go to 0, then heads go to 1, tails go to 0. So I do this thousands of times. Roughly, tails have seen half of the times 0 and half of the times 1. Heads have seen half of the time 0, half of the time 1. The best thing I can get is that whether I get heads or tails, the best thing in expectation is what? Half. Okay? So this is why my proposal was very bad. You don't have this multimodality. The model doesn't understand that there is more than one possible solution. Okay? You kind of like saying there is only one possible solution, and then this one possible solution is going to be this sampling. And if you wouldn't have used MSE, say you used L1 instead of MSE, like Manhattan distance, you know, and anyone knows what would you get? It's not going to be the expectation, the median, right? Exactly. Okay. Which brings us to generative adversarial networks. So it was like the most popular generative until the diffusion models got big. People didn't look at VAEs anymore. They all only loved GANs, and at least until the end of the last decade, it grew really, really big. And this is Ian Goodfellow who invented GANs in 2014. So to understand GANs, I'm going to ask you this question. What makes a good counterfeiter? I want to make fake money. Okay? How can you evaluate how good I am at my job?
People accept your money.
Okay, but you know, some people are stupid. Not here. Here everyone's smart. Some people outside of this class. So
That's
I
like
know.
the class of mathematicians.
I can pay half of the people with monopoly money. Okay.
Banks accept your money.
Sorry?
Banks accept your money.
Okay, that's a good direction. Or I would say, if someone that his job is to identify fake money is being fooled by me. And the better this guy is in his job, and I was able to fool him, I'm better in my job, right? So to make it more compact, what makes a good counterfeiter is one that can fool a good cop. Okay, you're with me? This is the basic idea. So we're not going to call them counterfeiter and cop. We're going to call them generator and discriminator. The generator generates fake data, and the discriminator wants to say whether or not this data is real.
How susceptible is the discriminator to adversarial examples in this case?
How what? Sorry?
Like how susceptible is the discriminator in this case to examples that are not really the image you want to generate, but
Okay,
classify.
so let's see in a minute, we'll understand how it works, okay? So we have the generator and the discriminator, and we're not in the criminology business, we're in the AI business, so they're going to be networks. So basically, GANs, generative adversarial networks, are going to be networks competing each other, and let's see how it works. This is a very, very elegant idea from a decade ago. You have a data set, okay? The first thing we're going to do is to train the discriminator. Are we all good? So I sample an image, the image goes into the discriminator. The discriminator is going to be a binary classifier network. It only has to say whether or not it's real or fake. So when I provide a real image to it, okay, I'm going to use the label of 1, saying, yes, this is true. And now the discriminator has seen a real example with the label 1. This is just supervised learning for it, okay? And if you're using cross entropy or binary cross entropy in this case, so this means that I'm maximizing the log of d of x given that x is a real example. Okay? It means that like 1 is I think it's the most real possible, 0 I think it's the most fake possible, and everything in the middle is I'm not sure. Okay? So for a real example, when x means real, x coming from the data, I want to maximize d. Maximize d, maximize log d is the same thing. We good? Okay. Now, this classifier has seen a real example. What else does it have to see? A fake example. Where do you get fake examples? Sorry?
The generator.
From the generator, yeah. So, okay, I forgot to say, we train it, we update the weights, okay. Now, I need to see fake examples. And the way to get fake examples is from the generator. So I sample noise, I take it into the generator produces something. In the beginning of training, it may be something very bad. As training progresses, we'll see, the generator may be very good and produce good fake examples, okay? It gives me something, and then I train the discriminator, but now I say, okay, I know that this is fake, so I'm going to train the discriminator with the label of 0. Are we good? Okay by now? What you have to watch out here is that now we're going to do this backpropagation. Don't do the mistake of letting the gradients go into the generator. We're only training the discriminator for this. You don't train the generator using anything of this. So in PyTorch, it's going to be like detach. The vector goes into the discriminator dot detach. So it means that gradients don't flow back. And what I got here now is saying that we had this before. So for the real data, I want to maximize d of x. For the fake data, what is fake data? Fake data is g of z, right? Generator of z. And d of the fake data, I want to minimize it. So I take 1 minus it and log. Okay, log 1 minus something is minimizing it is like minimizing d. Okay, we're good? All right. Just when you use cross entropy, this is what you get. Okay. Okay, great. This is how we train the discriminator, but we also have to train the generator, right? So, how do we train the generator? So, this is the tricky part. Remember what we said? That a good counterfeiter is one that can fool a good cup. A good generator fools a good discriminator. There is no way for us to train the generator without using the discriminator. Let's see how it works. So look at the math here. We said we were maximizing. This is just basically classification, maximizing the classification when g of z is the fake examples and x is the good examples. But look at what I'm adding here. This becomes min max. Okay? If someone here takes courses in game theory, then you've seen this. Okay, this is called a minimax game. So this is exactly the generator trying to fool the discriminator. Remember, a good counterfeiter fools a good cop. So this is being a good cop. Okay, this max. I'm trying to be the best cop that I can, the best in my job at finding fake money. And then the generator says, yeah, but given this best cop, okay, the best cop that there can be, I want him to make the biggest mistake. I'm going to fake my money so well that this great cop is going to believe me. So I'm going to minimize his grade at finding fake money, given that he's good, using my very, very, very good fake money. Okay? So how do I do this? Now I'm going to generate an image. Okay? The image goes into the discriminator. And look at what's going to happen now. The generator says, I want to fool the discriminator. So this is a fake image, but the label that I'm going to provide now is the label 1. Like it's a real image. But the thing you have to remember is that I'm not training the discriminator now. I'm training the generator. So I'm going to backprop, and I'm just going to use this to get the gradients here. But I'm not going to update the weights of the discriminator using the gradient that I got from training the generator. In fact, they're going to have, when you implement such a thing, they're going to have 2 different optimizers. You've used optimizers in Python, right? So each of them, there is going to be the optimizer for this and the optimizer for this, and the optimizer for the discriminator is not going to do anything now. Okay? The only reason you see the backpropagation goes here is that this is the only way I have to calculate the gradient with respect to the weights here. Think about the discriminator in this case as these complicated loss functions. Sometimes you use MSE, sometimes you use something else. Now you're using the discriminator, and you use it as a frozen thing that you know how to take the derivative of using backpropagation, but you're not optimizing it now. Okay, it's just a very nice and special loss function.
Why do you pass the label 1?
Sorry? Oh, because I want to fool it. I'm saying I'm giving a fake image such that the discriminator would think that it is real. Okay? This is my goal. I want to make fake money. I want to give it to the cop, and I want the cop to say this is real. Okay, if the cop said no, that's not real, and I can't do it in real life, but with gradients I sort of can. I can ask him, well, why did you think it wasn't real? And he said, I look at the light and I didn't see whatever Golda Meir, or I don't remember who's there anymore, and I didn't see Golda Meir, okay, and then I get these gradients, and say, oh, okay, I'm going to add Golda, okay, and then let's do it again. Okay, so a few questions can arise here. My question to you, first question, who do you train first? Generator or discriminator? Okay, the answer is you do alternate training. So you're going to do GD, GD. Okay, maybe you already knew this and you thought I was asking if you do GD, GD or DG, DG. Yeah, it doesn't matter. Okay. But the thing is, you do this alternating. Okay, why does it work? So I try to convey the reasons it works already, but here are a few other thoughts that may help you understand. So D learns probability. Okay, D looks at reals and fakes and learns kind of a number between 0 and 1 to say how real an image, I believe an image is. Okay, and once I have this sort of probability, G uses D and tries to maximize the probability of the realness of what he generated. So G looks at D and say, I want to generate an image such that D grants it the highest number possible. Okay, good so far? Next, there is, like in contrary to my very bad suggestion from before, we don't predetermine those pairs of saying this noise is going to go with this image. I'm not saying this at all. So the space is going to be arranged by the model itself. Because I never say what's the explicit image that this noise is going to map to. All I'm saying, which is very clever, think about it, given this noise, I want to generate something, whatever, that the discriminator likes. I'm not going to tell you which image it's going to be. Do whatever you want. Just make the discriminator like it. So it's naturally going to be spread in such a way and not going to have this centroid, this center of mass we've seen before. And then if you look at the main paper by Ian Goodfellow, there is a very nice short proof that under ideal assumptions, you actually minimize. So JS is the Jensen-Shannon divergence, which is kind of the KL divergence, but the symmetric version. So KL divergence is not symmetric, and Jensen-Shannon divergence is like KL this way plus KL the other way, half. Okay, like making this symmetric. So there is a very short proof. It's really nice and easy proof that shows that if everything is ideal, like the gradients are the models are infinite, you have infinite data, whatever. So then you're actually going to minimize the distance between the distribution of what you generate and the true distribution of the data. Okay. Frequently asked question number 2. Always people try to kind of ask why you do this alternating, because there are a lot of problems with it, and do you have to do this? Why can't you just train the discriminator first or whatever? Okay. So first thing you have to see is that gradients are meaningless when the game is unbalanced. Okay, if I'm going to play one-on-one with Steph Curry, I'm not going to learn a lot. It's just going to run dunk over me, whatever. It's not going to dunk. Doesn't dunk, right? Okay, I'm going to shoot like 3 points all the time above my head, and I'm not going to learn anything of it. So this is like in the philosophical sense. But let's just try to make this thought experiment. Okay. Okay, let's pre-train B. Okay, let's start by pre-training the discriminator. All right, I use the data as the positive example, right? It's true. What is I don't have negative examples, right? Because if I didn't train the generator at all, it's going to produce nothing, but like noise. And then all D is going to learn is how to distinct real images from noise. But his job is should be much harder. Okay, it's like the cop learning how to discriminate real money from, I don't know, from dirt from the floor. Okay, no, you have to be good at discriminating real from good quality fakes. Otherwise, the fakes are not going to get any better. Okay, pre-train G. Fine. With what loss? If I don't train the discriminator, I don't have any loss that makes sense. It's like instead of giving my money to the cop to check it, I'm giving it to like I don't know, to a dog. Okay, and ask the dog if it's okay, because real people, they can give you some kind of okay. I show this money to the dog. Is it real? I don't want to offend dogs. I don't know. I'll get canceled. Not a dog. Whatever. Something that doesn't know about money. Okay. Okay. So yeah.
We try to balance the game other aspects like parameters of network structure or something like that.
Yeah. I mean, yeah. I'll get in a second. I'll show some really unpleasant things. Yeah.
We saw 2 lessons how there's like for the best classifiers, there's always like these adversarial examples that it's just a picture of the data.
Yeah.
How, like I imagine the discriminator is also susceptible to those.
Yeah.
How do we know that the generator doesn't generate adversarial examples instead of real images?
Because if it does, the discriminator learns to identify the adversarial examples. You see, if you train, even in the adversarial world, if you have pre-made adversarial examples, then you can learn to to discriminate, right? So,
Through a long training course, you get much more negative examples than positive examples because the generator is constantly making more zero, like mislabeled data, and you only have a certain amount of.
What I mean mislabeled, there are no label. I don't know.
Wouldn't the continued training on D, the discriminator, be the generated examples?
Yeah, you just keep going both on the real examples and the generated examples. All right. So this is what you could get in 2014. So these are MNIST. So on the right is like the nearest neighbor of the almost to the right. For some reason they wanted to show it. So you can see some grayscale faces. You can see digits, and then these are CFAR. Not so great, but in 2014 it was very exciting. And then a year after, Alec Radford used convolutional network for the GAN, and it got better results. So nice looking faces, and they could show this nice property. It's called latent space mapping. So the thing you do, you sample noise, and you sample another noise. Then you draw a line between them on the latent space, and you divide it to whatever 100 or 1000, and you do tack, 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 along this line, and you get this continuous changing phase. Why would this work? And the reason it works is that it's just two facts. Say you trained your GAN right, okay? Everything works. So every point is mapped to a valid example. Whenever you sample something from your latent distribution, you're going to get a valid example. And the second thing, neural networks, almost all neural networks and everything we're familiar with, like at this point in our course, are continuous functions. Think about it. You multiply by matrix, okay, continuous. ReLU, continuous. What else do you have? Software, whatever. Everything is continuous, okay? So if it's continuous, from the definition of continuous functions, right? If you change the latent space by a little, it means that you change the result by a little. If you really want to get petty, so it's not the continuous thing, it's Lipschitzness. It's like a Lipschitz function, okay? All right. Here are some evaluation metrics. So I'm going to skip this thing that's called Inception score. You can read about it. It's less important, and I don't want us to end without seeing it. Oh, you know what? How many ends do I have? Okay, no, I'm going to skip it. Okay, but this is an important metric. This is to this day the metric that people use. So now you have your generative model and you want to evaluate. Okay, and this is kind of like the numbers you're going to show in the paper. It's called FID, Frechet Inception Distance, and here's how it works. You take some real images from the data set, and then it goes to this network that was trained for classification. It's a specific network by Google. It's called Inception network. This is why it's called Frechet Inception Distance. And then you take these, representation layer somewhere close to the end here, okay? But not the class, of course, but somewhere from there, and you just fit a Gaussian to all this data. You take a lot of data, it goes through, you get a lot of vectors for this layer here, and you fit a Gaussian. Fit just one single Gaussian. Okay, you calculate mean, you calculate the covariance matrix, you fit it, you get one multivariate Gaussian. Okay? But now you're going to do the same with your generated data. Okay? So the idea is that the network kind of gives this perceptual representation to those images. It doesn't matter if real or generated images. And now you have two Gaussians, and you want these Gaussians to be close. And the way you do this is with something called Frechet distance. And the reason, again, you can do it easily is that Frechet distance between Gaussians has a closed form. Okay, you do all this magic with the difference of the means, and then the place for the variances. You can analyze Frechet distance later if you want. But the basic intuition, it's kind of, if you have two distributions, you can think of you walk your dog, and you walk on one distribution, and the dog goes goes on another, and what is this maximum distance that you get, not necessarily a vertical line between them. Okay, what would be the maximal length of the leash? It's a very high level, but you can read about Frechet distance. But the thing is that it's a distance between distributions, and for Gaussians, it has a closed form. Okay, so this is FID. One important thing to remember, because this can make problems for you, is that FID depends on the number of samples. So you would usually want to do this. It will take you some time. You want to evaluate using something like 50K examples, because if you do less, you might get lower FID than what you actually deserve. Okay, because think about it. You'll have the estimation of the Gaussian, you'll have variance of the estimation of the Gaussian itself, and you can see if you don't use enough examples, it's going to hurt you. Okay. Now, another thing that was invented at some point by Philip Isola in 2016 was image-to-image translation with conditional GANs. And the idea is that I don't want to just sample from the distribution. I want to have conditional sampling. So instead of just noise to image, I want to have some signal in one domain and do it some kind of domain transfer to another domain. So this is sketch to real looking shoe, or whatever, map to satellite, day to night, low resolution to high resolution. Okay, so it really works in a simple manner. So it's the basic GAN as we've seen before, with one difference. Instead of noise going here, there is a signal going here. But the signal also goes to the discriminator, because the discriminator has to judge the distribution conditioned on the signal. It doesn't have to say, do I believe this is a real shoe? It needs to say, given this sketch of a shoe, do I believe that this is a plausible shoe that both matches the sketch and looks real? Okay, we good? And then if you look at this minimax game, it just has this tiny difference. So the discriminator always gets not just what we called X before, we call it Y now, like the jet, there is like Y real and Y jet and Y fake. Okay, it also gets the condition, and it gets it here, and it's not noise, it's X the input. Yeah.
To train the discriminator, you need to have a lot of examples of sketches to.
Right. Yeah. So this is basically built as supervised learning, right? You need to have pairs. Yeah. So you have a data set of pairs, and this is how it works. You train the generator to go from to generate. You give it X the sketch, and you train the discriminator given these pairs to say true pairs are real and fake pairs are not real. Okay, so you see, when you train it for fake things, or when you train the generator, so you use the same signal, the same input, but the generated image. Okay, and the discriminator, and when you train the discriminator, you say this is fake. When you train the generator, you say here this is real. And for the real examples, you just take those pairs out of your data set. Okay, you also use, you can also add this supervised loss like L1 between them, and it sometimes helps. And you combine this. And you can do this to many things, to whatever sketches and day to night and labels to street scene and things. And if you go to this website, you can paint things, and then it changes them to like real. But there is one particular example that will be a canonical example for us to learn from. And this is the colorization. There is something to learn here. And here's a question I want to ask you. So what's your name? Sorry?
Sammy.
So as Sammy pointed out, this is just supervised learning, right? What I just showed you. I took pairs. So why don't we just do supervised learning? So there is an input, there's an output, there's a true label, let's take MSE, whatever, and train this. Okay, because these are pairs. We actually have the pairs. Why do I need all this GAN mumbo jumbo? Any idea?
Want to be able to generate different arrays of colors. The thing is not.
Let's try to think about the conditional probability here and ask this question. If you didn't see this, and there are many examples in the data set, I'm seeing this grayscale butterfly. What color am I going to grant it if I just train it with supervised learning? Any idea?
Gray.
Probably grayish, right? Because when you train it, you've seen many butterflies. Some were yellow, some were red, whatever. Eventually, when you do supervised learning, you go to this centroid. The best thing you can do, if you want to be right for all of them, think about the loss. There is the distance from the time I saw it red. There is the distance from the time I saw it green. All those distances, I want to minimize the average distance to all these examples. So I'm going to be somewhere in the middle. I'm going to be in the expectation point, right? And if it was L1, I'm going to be in the median, as you mentioned, and whatever I do, I'm going to be in some sort of centroid. This is like the reason you want generative models is exactly this. You have this, it kind of reminds the coin toss I mentioned before too. Okay, let's say this is the true probability of the data, which is kind of what, let's say, you know, two possible colors of butterflies or whatever. Okay, and these you see examples drawn from this distribution. So some examples are here, some are here. The best thing you're going to do if you don't have a generative model, if you have like a discriminative model, is here, which is something that is unlikely. So I don't know, so there are gray butterflies, but let's say the weren't, because I can think of a better example. Say all butterflies are colorful, okay? You're going to only say that butterflies are gray, which is unlikely thing, but it's the best center of mass. It's the best compromise to all the data I've seen. You don't want to compromise. You want to say, I know it's multimodal. I know there is a variety of examples, and there is a distribution that I want to sample from and get these examples, not this centroid here. Okay, and you need this for most of the things you would do in computer vision. Let's say I do denoising. I have a noisy image, I want to denoise it. There are many, it's what we call ill-posed problem. There are many possible solutions, right? I want to be aware of the distribution of these possible solutions. I don't want to go to the mean of all of them. This is why in many like low-level vision things, you would get blurry things because you kind of take the average of all the possible solutions. Okay? So this is a strong message that I want to convey. Are we? Okay. I want to say that training GANs is hard. It's very hard and it can be very exhausting. So, and there are several reasons for why it would be so hard. So the first thing is stability. You have the generator and you have the discriminator, and they're fighting. Each one is trying to win, and it could be that the discriminator crushes the generator and you get nothing. It's kind of, so you can't stop the process. So if the it's like, you know, you're playing against someone that is not yet Steph Curry, but is growing to be Steph Curry as you play. And at some point it becomes Steph Curry and you are just me, and then you're lost. You can't win anymore. Or the other way around. And the other thing is called mode collapse. This is something you should know about. So we never explicitly enforced to have all the possibilities of the solutions. So let me explain what I mean. Say we have a 2D distribution that looks like this. And the generator trains, this is like a real experiment. And eventually the generator, these are a bunch of examples that the generator provided us, looks like this. It's called mode collapse because it only chose one mode from all these distribution modes. And think about it. The discriminator sees this and says, fine, go ahead. This is a real example, this is a real example, this is a real example. I'm good. Nobody is saying, yeah, these are all real examples. But there are other real examples that you didn't provide. There are other areas in the distribution that you didn't output. Okay? And this is called mode collapse. And you do a bunch of things against it sometimes, but you should know it's a problem. It's one of the biggest problems in GANs. Okay. Another thing is that GANs can overtrain. Okay? And it goes together with this thing, is that losses don't reflect anything. So you usually produce this kind of looking at the discriminator loss and for fake or for real and the generator loss. And you see, these are losses. So you're used to looking at the classifier training and the loss goes like this, right? But here, I don't know. I see two networks fighting each other, and it's a zero-sum game, if you know game theory. So if the generator gets good score, it means the discriminator gets bad score. So what you really want is them to be balanced. If one of them goes down and the other goes up, you know you're screwed. But if you see them balanced, that's it. You don't know what's going on anymore. Okay, fine, they're balanced, but nothing is changing, and you don't know because the copy is getting good. Sorry. The copy is getting better, and the counterfeiter is getting better. So okay, so it's like it's like two kids are playing. They're very bad at basketball, and the difference between their scores is going to be the same as I don't know if Steph Curry plays against LeBron James. Okay, so it can be both very good or both very bad. Okay, but and you're still going to see this, which brings us to this fact that GANs can overtrain. So you train, images starting to look good, and then everything goes. So it's really hard to do with GANs. You had a question there?
You have more external measurement.
You can, but it's kind of, so you can calculate FID or things like this. It takes a lot of time, and you do this. If you have a really long training thing going on, then you can, and you have more GPUs to use, you can kind of run the evaluation, and then it takes some time, and then we'll see. But it's not like this thing that's, like a loss that at every point, but you don't know when to stop. I mean, you can, you keep snapshots and you try to do evaluations. Okay, I want to say a few quick things about GAN losses. So at some point in history, somebody came up with a thing called Wasserstein GAN, and I'm not going to get into the details. They said, okay, forget about the log, and we'll do this. And then whenever somebody comes up with a new loss, they also prove things, and they were able to show that this minimizes the thing called Earth mover distance. If you don't know what it is, it's kind of if you have two distributions, you can ask how much work it would take if these were like piles of sand. Sorry. How much work would it take to change this pile of sand, to take this pile of sand to be this pile of sand? Okay, and they were able to prove that it is. But my point here, I don't have a lot of time, so just want to make a few quick points. Then over the years, a lot of people came with a lot of GAN losses and all had like a proof showing something that it minimizes, okay? With all great ideas. So Wasserstein GAN is one of them. And then there were another useful one was it's called least squares GAN. So you see it's like it has this just square quadratic loss. Are any of these better? So I don't really know, but then at some point, 2018, in Google, they had a lot of compute and they did these experiments, and they had this paper, it's called Are GANs Created Equal? So they took this bunch of GAN losses, and even a VAE there, and they did like hyperparameters, this hyperparameter search. So they ran each GAN on, like, I don't remember, like they took 100 hyperparameters and changed all of them. So they did many experiments. And what you see is the FID, so lower is better, okay? And there are three different data sets that they generate. And what you see, like the colored part is like 1 sigma of all the experiments, like the Gaussian of all the experiments. And what you see is that nobody actually wins. So you can look at the line in the middle is like the average. So if you look across different data sets, in different data sets, different losses, different methods got an average that is different. You can judge according to the best performance. Okay, so you take this spot. This is like 2 sigma, I think, or or the very low, the lowest FID they could get on all the experiments. Again, nobody is really bleeding, okay? And one thing I like in particularly is the black star. You see this black star each one of them has? This is what they actually got when they published the paper about it. So this kind of shows you how hard the poor students had to work, like how many experiments they did. So if someone has their star close to the bottom, so yeah, they ran many experiments. They went through all the hyperparameters, and then there are where the black star is up. These are the lazier ones. They got okay. We got and how did this start happen? Like if you look at the axis of time. So think about how people work. So some guy did again and say, okay, let's invent something. Here is my Wasserstein GAN, and I'm going to work. And when am I going to stop working? Once I get FID that is better than the previous one, right? And this is the real bias of it. So, and this is fine. Okay, you can do this, and then you have the model that does better. But then people come up with the stories. Oh, it worked better because I don't know, whatever, Earth mover distance. Okay. But no. So if I have one message in this topic for you to take on is that this is usually what people would do. The way it looks is that you find the state of the art, you find the code, you take it, you do some changes. If it works, you do more changes until you get better FID, and then you publish it. Okay, so this is bad practice that is now happening. Okay, I really have. Okay, I'm going to take this like 3 minutes after time. Is that okay? So somebody. Okay, because I do want to mention that these people from NVIDIA back in 2018, Terracross, they came up with the idea of progressive growth. So it basically means, I'll show you the animation, you start training with low resolution, and you see after a day, you add more layers and more layers that increase the resolution. And this was like a big breakthrough that enabled GANs to work for really nice, high resolution, very realistic images. And then they improved the progressive growing with thing called, and this is like the most famous and useful GAN. It's called SyleGAN, and SyleGAN is using this layer called ADA-INS, adaptive instance normalization. These are like tricks that you can read about. I'm mentioning this because they had big impact. It's not something that is conceptually very hard. But the idea was that the noise goes through all the layers, and it uses this instead of just as inputs, it's used as a normalizing. So like you do batch normalization, it's instant normalization. It's only normalizing at each instance separately. But the thing is that you get the noise in, and the noise kind of sets mean and variance that renormalizes at every different layer. And this has this nice property of where different layers you control different elements. So if you go in deeper layers, you change textures, and if you go to the first layers, you kind of change the structure. So and then you can mix between different phases, and it looks hyper realistic. And here's another example for the different attributions. So if you change the low resolution, you see it changes like the gender and the structure and everything. If you take the middle, you change like the middle attributes, and then you only change sort of colors and very fine textures. And after that came out, there were all these websites like this person does not exist, and you just go to this person does not exist.com, and every time it gives you a picture of a person that doesn't exist. And you can do a nice thing. I want to do this together with you, but unfortunately we don't have the time. There is a nice thing called does this person exist, or is this person real? I don't see it here. That you can go to, or which face is real. And there are two faces, one is real, one is not, and you have to guess which one. And I'm going to skip this GAN dissection thing. We need to really end. We'll just end by mentioning one thing that happened by people involved in this course. So at some point we were able to train GANs on a single image, and the idea was that you take an input image, just one single input image, you take it into a generator, the generator does something to it, and the discriminator, instead of producing one number, produces a map. And the map kind of judges each patch in the size of the receptive field of the discriminator, whether it believes it came from a generated image or from the real image. And the generator tries to change the image in such a way that it's somehow different, but in the patch level, the discriminator cannot discriminate between generated patches and the real patches. And then you get things that look like this. So this was my own work a few years ago with the Shai, with Philip Isola, and with the Michal, and also Tali had a similar work with the Tamar Chacham and Tomer Michael from the Technion, and they actually got the best paper award for it in some year. And here's an example of things you can do to use this food standard. This is from 2018, I think. So you change this fruit stand, and it's kind of, you keep the DNA of the image. It's the same. It has the same patches, but it just can be arranged differently. So kind of you can change the geometry, but you still get things that make sense. And if you need, you add fruit, you remove fruit, you add crates, and everything happens just because whatever you see generated is just that discriminator that looks kind of, a very narrow vision, can tell the difference if this patch was from the original image or from the fake image. Sorry for taking 5 minutes more of your time. I want to thank all of you. This was my last lesson in this course, so thank you all for it was really nice teaching you. You had nice questions and insights, and I was learning from you guys too. Good luck in your projects and everything.